This city, the people in it, in fact, all life on the planet are only here by chance. 99% of all the species that ever existed were wiped out in a series of global catastrophes, disasters that changed the course of evolution. But without them, we wouldn't be here at all. 250 million years ago, the largest volcanic eruptions the planet had ever seen nearly erased all life on Earth. This is the story of Fireball Earth. I'd always thought that our rise to become the dominant species on the planet must have been a fairly orderly progression from species to species. But it wasn't. It was an arbitrary, often brutal process, a case of survive or die. It's difficult to grasp the immense timescale of the events that shaped us. So imagine Earth's history, all 4.5 billion years of it, compressed into the 24 hours of a single day. Each minute is 3 million years. At midnight, the planet was born. At 12:02, we suffered our first catastrophe. Earth collided with another planet, Theia. Our planet was nearly destroyed, but in its wake, life began. Billions of years passed. Then, at 8:27 p.m, Earth was encased in ice for millions of years. Primitive life in the oceans was pushed to the brink. But when the ice melted, life took its greatest ever evolutionary leap, from single-cell to multicellular organisms. And then things calmed down. But not for long. 10:40 p.m. on our clock, that's 250 million years ago, once again, every living thing faced extinction. It's a period in prehistory called the Permian, and the Earth faced the biggest catastrophe it had ever seen. One cataclysmic event kick-started a chain reaction that wiped out 95% of all the animal and plant species on the planet. It was Earth's darkest hour, according to scientists like South African paleontologist Roger Smith.
The end Permian extinction was as dramatic as a mass extinction could be. Since the beginning of life on Earth, there has been no other one that has come close to the 95% of species on Earth, both in land and sea, disappearing within a very short space of time.
It was the worst mass extinction ever. But without it, the world we recognise today wouldn't exist.
Had it not been for those few survivors, those few animals which were pre-adapted or able to get through that great drought, we would not have had life on Earth.
How it happened, why it happened, it's a mystery that's puzzled scientists since evidence of the catastrophe was first discovered almost half a century ago. If they could solve it, it could shed new light on our understanding of the evolution of life on Earth. In South Africa, 3 hours' drive from Bloemfontein, Roger Smith is visiting an area that was once teeming with animals.
We're here in the Karoo Basin of South Africa, and it's a vast semi-arid scrubland, lots of canyons, lots of koppies, these flat-topped koppies. But 250 million years ago, this would have looked a very different place. Rainfall in the mountain areas were feeding Mississippi-sized rivers which meandered themselves slowly across the plains. This was a fully developed, stable ecosystem.
Small plant-eating creatures called Dicynodonts thrived here, scurrying about in the vegetation. Huge herds of cow-sized herbivores called Dicynodonts grazed on the plains. But this flourishing world was also home to a vicious killer. Over 150 million years before T-Rex came along, Gorgonopsian was the Earth's most efficient carnivore. Armed with serrated interlocking teeth, this ferocious animal was the ancient world's top predator. But all these creatures were doomed. None of them survived the mass extinction. An event so devastating, so total, life itself was nearly wiped out. Its cause would be a mystery. If it wasn't for clues buried in the rocks, like those of South Africa's Karoo Basin. Under this scrub, paleontologists have unearthed rocks from this turbulent time.
My job as a geologist and a paleontologist is to read the rocks and to understand how they were laid down and to understand what happened to life through the ages. Now, sedimentary rocks like this are characterized by layers, each layer representing a point in time when deposition was taking place. The oldest layers are at the bottom and the youngest layers at the top.
These rocks are like a time machine, taking us back 250 million years. As Smith climbs the rocks, he reaches the layer that records the moment the Permian world was wiped out.
Here we're sitting at the very top of the Permian, and this particular interval shows us something very dramatic in the rock record. Below me, we have green and bluish-grey rocks that clearly suggest that the environment was wet.
These rocks testify to the near death of our planet. The grey and green rocks were formed by flooding, and they're littered with fossils. They tell us that this part of the world was once wet, lush, and full of life. But just above this layer, it's a very different story.
Suddenly, everything turns red, and that reddening is an indication of drying, rapid drying and warming.
These red rocks reveal a sudden and dramatic rise in temperature and mark the point in time when life on Earth very nearly came to an end.
The fossils tell us at this point there is virtually nothing left on Earth and we go into a dead zone.
This layer marks the moment when the world changed. Below the line, grey rocks full of fossils, full of life. Above, in the red rocks, nothing. Life had almost ceased to exist. And not just here. The dead zone was a line of death that travelled all around the world and could be found on every continent. This meant that global warming and mass extinction were global. 250 million years ago, the Earth's temperature spiraled out of control. Something huge on a planet-wide scale pushed temperatures up by 10 degrees and killed virtually all life on Earth. It's 10:40 on our clock of the Earth's history. 250 million years ago, our planet was in climate free fall. The sudden and dramatic global warming changed the course of evolution on Earth. It caused a mass extinction so devastating that scientists thought it must have been caused by something extraordinary. An impact from outer space. Could it have been an asteroid strike? An impact would have sent billions of tons of dust high into the atmosphere. blocking out the sun, stopping plant growth, reducing temperatures, and causing the food chain to collapse. The extinction would have happened within days, weeks, but that's not the story the rocks are telling us. Over the last decade, Professor Paul Wignall and researchers at Leeds University have been examining rocks from the dead zone around the time of the devastating mass extinction. They've collected thousands of samples and taken hours of video on their expeditions to Greenland. These rocks paint a more complete picture of the extinction than the rocks from South Africa, revealing a story of extinction on land and sea.
The extinction is like the biggest fossil crime scene of all time. And so the great thing about Greenland is that we have such a great record at the crime scene, if you like. There's just a huge amount of information to be collected. So it provides us with an extremely detailed record of what happened, probably one of the best records of that time interval.
What's more, these Greenland rocks put paid to the idea that an impact caused the extinction.
One of the most obvious clues would be that the extinction should occur extremely fast, within sort of days and weeks of an impact. Everything will essentially drop dead in a matter of years. And so that should be razor sharp when we see it in a fossil record. We should see just an abrupt line or termination, and that's not what we see.
Instead, Wignall's rocks show that the extinction happened over a period of 100,000 years. Far too long to be the result of a meteor strike. The Greenland team's discovery meant that something else must have caused the catastrophic extinction. And geologist Mike Benton thinks he knows what. He believes the disaster began deep beneath the Earth's surface.
If it's not impact, then the next most obvious, dramatic, instant kind of catastrophe is initiated by volcanic eruptions of some kind. So you obviously look for some center of volcanic eruptions.
Volcanoes are nature's ultimate destructive force. Fueled by immense pressure deep within the planet, they shoot molten rock and toxic gases high into our atmosphere. If scientists could find evidence of intense volcanic activity taking place just before the mass extinction, then it could be the smoking gun they'd been looking for. Deep beneath the frozen wastes of one of the remotest corners of the Earth, Siberia, is a major clue. A vast expanse of ancient lava flows forming a bleak landscape called the Siberian Traps.
The Siberian Traps are a style of volcanism which we don't see on Earth today. They represent the biggest style of volcanism that the Earth ever experiences or produces.
Earth's ancient volcanic eruptions dwarf anything we might witness today. At the end of the Permian period, millions of cubic miles of magma built up beneath the Siberian crust. The entire region began to bulge upwards. And then, like a giant blister, the Earth erupted, spewing out vast amounts of lava, flooding the area under a sea of molten rock. It's a type of volcanic eruption called a flood basalt. Here was the force behind the extermination. 250 million years ago, the Siberian flood basalt released enough lava to cover an area the size of the United States under 1 mile of molten rock. Siberia has long since cooled, but Iceland is still one of the world's most geologically active places. Here, Mike Benton is researching the terrible impact even a small flood basalt could have.
We're here in the middle of a lava field in Laki in Iceland, because this is a very well-documented historical basalt eruption that can act as a good analogy for the Siberian Traps. In 1783, a vent eruption happened here which lasted for about 8 months.
This 18th century incident offers a unique insight into a flood basalt's devastating power. Over 8 months, the Laki event ravaged southern Iceland. But it was tiny compared to the Siberian eruptions. Even so, it was a disaster.
Volcanoes produce 3 things. The lava is one, that will kill things locally, but it produces ash and, most importantly, gas. Now, the lava goes a relatively short distance, the ash will go further, flying through the air, but what really kills are the gases.
The Laki eruption produced huge quantities of sulfur dioxide, a gas which has a deadly impact on the environment. Mixing it with water creates sulfuric acid, which falls to Earth as acid rain.
That has a terrible effect, as was recorded by the people at Laki, where they reported that it burned people's eyeballs, it made it hard for them to breathe because it congested their lungs. Livestock suffered lesions and burning of their skin, and plants were killed off.
The whole food chain began to collapse. And that was just the start. Some of the sulfuric acid didn't fall back to Earth. It stayed in the atmosphere in small droplets. These reflected sunlight away from the planet, cooling its surface.
The cooling following the Laki eruption was catastrophic. It killed more people than the immediate damage by sulfuric acid. It created very cold winters for 2 or 3 years after the eruption, not just on Iceland, but throughout much of northern Europe. People reported crop failures and death as a result.
Benton's analysis of the Laki eruption has shown that the cooling effect produced by volcanic sulfur dioxide is deadly. And that the effects can be felt thousands of miles away. Imagine how devastating the Siberian Traps must have been. Laki spewed out gas and lava for 8 months and covered an area of about 200 square miles in molten rock. But the Siberian Traps erupted for nearly 500,000 years. They produced almost 3 million square miles of lava. That's 200,000 times larger than Laki. Using Laki as a model, Benton can begin to reconstruct the chain of events that turned the Siberian eruptions into a global killer. It started with a huge eruption.
The most likely sequence of events starts with these massive eruptions in Siberia, with lava spreading over thousands of square kilometers, square miles of landscape, and causing destruction and devastation wherever they went.
Then came the real killer. Like Laki, the eruptions released billions of tons of sulfur dioxide into Earth's atmosphere. First, it turned into acid rain and bleached vast areas of the Earth. Then it created volcanic winters, which sent global temperatures plummeting. Around the world, the climate change killed plants, and the food chain fell apart. Where the plants failed, herbivores like Dicynodonts starved. And where they starved, the carnivores that ate them died too. 10% of species perished. But this was just the beginning. Another gas released by the Siberian Traps was about to make things much, much worse. In Leeds, paleontologist Paul Wignall is surrounded by the victims. Fossils found in rocks from Greenland. They testify to the devastating effects of the Siberian eruptions.
The first things that start suffering in the entire fossil record is the plant record. We start seeing a change in the composition of plants. And also we start to see the appearance of some very strange mutated spores.
Wignall's fossilised plants reveal a world struggling to adapt to climate change. They also record the effects of a second deadly volcanic gas: carbon dioxide.
Looking at the surfaces of leaves and the number of little holes that are in the surfaces of leaves is actually a monitor of how much carbon dioxide there is.
Plants need carbon dioxide to survive. They absorb it through tiny holes on the backs of their leaves. The more carbon dioxide there is in the environment, the fewer holes the plant needs to absorb it. When scientists studied fossilised leaves dating back 250 million years, they discovered a sudden dramatic reduction in the number of breathing holes. It seemed that at the start of the extinction, levels of carbon dioxide surged. And that meant one thing: the Siberian Trap eruptions must have released billions of tons of CO2. Scientists calculate that the amount of carbon dioxide in Earth's atmosphere at the time of the eruptions was 20 times higher than it is today. More than enough to seriously affect the climate. It was global warming gone mad.
The result of these Siberian Trap eruptions was a rise in global temperature of at least 5 degrees centigrade. And they happened episodically, so that it may be there were pulses repeated and repeated of temperature rise.
5 degrees may sound small to us, but it had a massive impact on the Earth's climate. Warming the Earth's atmosphere affects how rain is generated and dictates where it falls. By raising the Earth's temperature, volcanic CO2 fundamentally altered global weather systems. In equatorial regions, it simply stopped raining. In South Africa, the Karoo Basin felt the full impact of this change in climate. Its lush floodplains became a scorched desert. Paleontologist Roger Smith studies how this rapidly changing landscape affected the Karoo's inhabitants. And he's just discovered one of the victims.
Here we have an in situ skull of Dicynodon. It's one of the last of the big cow-sized herbivores of the Permian period. And at this level, which is just below the extinction, this represents probably the last gasp of the Permian herbivores.
The global warming marked an evolutionary watershed in the Earth's history. Animals and plants suffered from drought and starvation. 35% of them perished. But the fallout from the Siberian Traps was only just beginning. The rise in global temperatures triggered a domino effect that unleashed the next terrible wave of extinction, this time in the oceans. It's 10:40 p.m. on the Earth's clock, 250 million years ago. Massive volcanic eruptions released millions of tons of gas that first cooled, then heated the ancient world. This seesawing climate killed animals and plants by the million. Extinction ruled the land. This was the terrible first phase in the extermination of virtually all life on Earth, but a critical moment in the story of man's evolution. So far, the oceans had escaped unscathed. But that was about to change. Paleontologist Paul Wignall has found evidence of the next deadly phase of the mass extinction, 50,000 years after the start of the Siberian eruptions. The death of the oceans.
This is a really nice example of rocks that we get from Greenland. The evidence is, first of all, they're very black, which is typical when you have no oxygen around. But even more telltale is these lovely sort of golden crystals, which we can see on the surface. And this is pyrite, or fool's gold. And we'd only find this if there was no oxygen around on the sea floor.
It's an important breakthrough. Fool's gold can only form in an environment that lacks oxygen. Its discovery in 250-million-year-old rocks means only one thing. Somehow, the Earth's oceans had lost their oxygen.
It was clear that there was something major going on which hadn't been discovered before. What we could see was a sudden lack of oxygen at the end Permian mass extinction. It's a completely new extinction phenomenon. It's then that we realised that we were now looking at a very different way of killing life in the seas.
But even lower oxygen levels in the water can't explain why so many different species died. It's a mystery that research at Green Lakes National Park in upstate New York has helped to solve. Marine geologist Lee Kump has discovered the process that he thinks was responsible for the wipeout of nearly all marine life 250 million years ago.
We're here at Green Lake because we view this as a microcosm of the ocean that may have existed at the end of the Permian at the time of this great mass extinction. It's a really unique habitat here that's unusual in terms of most lakes. It's like a typical lake at the surface, but lurking down below is this poisonous water.
The lake looks normal, but under the surface it's dying. Just like the ancient Permian oceans. The water's stagnating, its circulation grinding to a halt. Over the past 5 years, Kump and divers from Penn State University have been monitoring the lake's slow death. At the bottom, they've found strange colonies of purple sulfur bacteria, an organism that only lives in water rich in a highly toxic gas called hydrogen sulfide. And this gas is a vital ingredient in the production of fool's gold, discovered in Greenland rocks from the sea floor 250 million years ago. It seems whatever is happening in this lake was happening in the Permian oceans.
Once the oxygen level drops, then to the point where there's no oxygen left, then organisms that can't stand oxygen begin to thrive. And these organisms have a waste product, hydrogen sulfide, that is poisonous to air-breathing life.
Kump and his team are researching the rising levels of hydrogen sulfide in the lake. They do this by measuring the growth of purple sulfur bacteria, recording the changing depth at which it can be found. They know when they found it when they pull out pink water.
We're looking for the pink water because that's indicative of where these purple sulfur bacteria live. So this is our marker of where these organisms have a very large population density. There are so many there that they create this pink water.
Below this toxic layer of pink water, oxygen-breathing animals can't survive. Kumps charted the changing depths at which pink water can be found in Green Lake.
Ready?
Ready. Whew. Oh, yeah, that's rotten eggs. That's nasty stuff.
He's discovered that as oxygen levels in the lake drop, the amount of poisonous hydrogen sulfide increases and pink water can be found closer to the surface. It means the poison is rising up through the water, killing all the oxygen-breathing animals who live there. The Green Lakes are just a few small pockets of water, but imagine it on a global scale.
If we were to take a satellite picture of the Permian Ocean, the regions that are green today would have been pink when viewed from space because of the abundance of the purple sulfur bacteria.
Kumps Green Lakes research gives us an insight into what was happening in the world's oceans at the time of the mass extinction. Rocks from the same period tell us it was a global phenomenon. Oceans and seas were starved of oxygen and saturated with poison. Something major must have happened to trigger the removal of oxygen. In Green Lake, it's caused by stagnating water. The water has stopped circulating. And recently, researchers have discovered that 250 million years ago, the same thing happened on a global scale. Normally, oxygen dissolves into seawater at the surface. It's then transported by currents circulating between the equator and the poles. Sunlight at the equator warms the seawater. As this warm water moves towards the poles, it cools and sinks, carrying its dissolved oxygen down with it, allowing the oceans and its inhabitants to breathe. This same process was happening 250 million years ago. But then, the Siberian Traps came along and raised Earth's temperature by 5 degrees centigrade.
The significance of that for the world as a whole, and particularly the oceans, is the way it affects circulation in the world's oceans. It's a bit like leaving a goldfish bowl in the window in bright sunshine. The water there, it warms up, it loses its oxygen, and it essentially stagnates. And so if you magnify that to an oceanic scale, then that's effectively what we think is happening in the oceans at the end of the Permian.
The evidence suggests that 250 million years ago, the rapid global warming created by volcanic gases warmed not only the atmosphere, it warmed the oceans. They stopped circulating oxygen and stagnated, becoming breeding grounds for poisonous hydrogen sulfide producing bacteria.
The warming then led to the development of the buildup of hydrogen sulfide in the deep ocean. This built up to such large concentrations that it invaded into the shallow part of the ocean and displaced all of the air-breathing organisms from those environments and eventually providing them no place of shelter.
Climate change triggered by the Siberian Traps had already killed around a third of all species on land. By raising the temperature of Earth's oceans, it then caused the death of virtually all life in the sea. But the killing wasn't finished. Lurking at the bottom of the oceans was another killer, one that would wipe out practically everything else on Earth. In Iceland, geologist Mike Benton is searching for clues to this final deadly wave of extinctions.
There is a mystery to understand how the production of carbon dioxide and the sudden rise in global temperature of about 5 degrees could have caused such a catastrophic event. A sudden rise in global temperature of about 5 degrees wouldn't in itself kill life in the catastrophic way we see. Something else must have caused that massive scale of extinction that we know happened that time.
The gases released from the Siberian Traps triggered global warming that wiped out species first on the land, then in the oceans. But then temperatures increased again by another 5 degrees. The result, a catastrophic second wave of extinction on the land. Scientists know that carbon dioxide released by the traps caused the first leap in global temperatures, but the second jump remained a puzzle. They needed to find something even stronger than CO2 that could have accelerated global warming on an unprecedented scale. And they found the answer to this mystery hidden in the depths of the ocean off the coast of Santa Barbara, California. About a mile offshore, Dr. Ira Leifer, a climatologist from the University of California, is on his way to monitor an unusual phenomenon. He's looking for another greenhouse gas, not carbon dioxide, but methane.
This area is where methane from deep within the Earth rises through the Earth's crust until it reaches the seabed, and then through the water column to reach the sea surface as bubbles.
You can find these bubble seeps in coastal areas all over the planet. But this one's proximity to Southern California has given scientists a unique opportunity to monitor one closely. In the cold North Pacific water, students from the university dive to the source of the seepage. They're going to gather samples of the gas as it escapes from the sea floor.
Methane is a very potent greenhouse gas, perhaps 20 to 25 times more potent on a molecule per molecule basis than CO2. That means if we add 1 molecule of CO2 to the atmosphere and 1 molecule of methane, that methane has 25 times the effect.
The amount of methane released by seeps like this one in Santa Barbara is too small to explain the additional 5-degree temperature rise recorded towards the end of the mass extinction. But there is another source of the gas that might. In the deep ocean, the most unexplored and least understood part of our world, lie vast quantities of a substance called methane hydrate. It's methane gas frozen in the cold water at the bottom of the sea. Today, there's an estimated 30 trillion tons of methane locked away in ice on the seabed. If it turned into gas, there'd be a global disaster. Ira Leifer thinks that this may be exactly what happened 250 million years ago.
If we look at this massive extinction as comparable to a genocidal crime on an unimaginable scale, and we ask ourselves, who are the criminal suspects? Who's responsible? We'd look at the evidence. And at the top of the short list is methane hydrates because of the vast size and their known instability.
Frozen methane is ultra-sensitive to heat. Raising its temperature by even a couple of degrees can destabilize it and trigger the release of this powerful greenhouse gas.
If the atmosphere warms for any particular reason, the ocean will warm, methane hydrate will release methane. This will warm the atmosphere, leading to warmer temperatures and even more methane hydrate releasing its methane to the atmosphere. A positive feedback cycle.
250 million years ago, billions of tons of volcanic gases produced by the Siberian Traps triggered one of these cycles. The eruptions increased global temperature by 5 degrees. The world warmed up, enough to thaw the frozen methane hydrate at the bottom of the oceans and release billions of tons of potent greenhouse gas into Earth's atmosphere. The temperature went up another 5 degrees. The world was now 10 degrees centigrade hotter. Unable to adapt to the extreme and rapid climate change, 95% of all life ceased to exist. But 5% lived, and those survivors are the ancestors of all life on Earth. "250 million years ago, a vibrant, lush ecosystem teeming with life was rapidly transformed into a barren, desolate world. For the planet's dominant species, there was no hope of survival. The planet had been brought to its knees by savage volcanic eruptions, turning it into a fireball Earth. The eruptions released toxic gases that created worldwide climate chaos and killed almost every living thing.
For something like a Gorgonopsian, it would have seen a world which would be changing. The various animals that it was eating would be becoming rarer. It would be getting a heck of a lot hotter. So terminal times for the Gorgonopsians and all around it as well.
For these fearsome predators, as for most living things, it was the end of the line. But in evolutionary terms, it was a new beginning.
Catastrophes can reset the evolutionary clock. That means that evolution, the whole direction of evolution perhaps will change because the dominant species disappear. And then other species that were taking a less significant role before the event have their chance.
These are cynodonts. They'd been a favourite snack for Gorgonopsians, but by burrowing underground, they'd stayed out of their predators' reach. And it proved to be a useful habit when climate change scorched the Earth's surface. Tubers and roots underground provided them with water and food. In South Africa's Karoo Basin, paleontologist Roger Smith has made a remarkable discovery.
We're looking at a burrow cast in the early Triassic, and we know from fossils that have been found in the ends of these casts that they are cynodont. Cynodonts were digging burrows during the end Permian extinction event. And it's very likely that that was one of the reasons why it was able to survive the Great Drought at that time.
After the mass extinction, these cynodonts went on to become one of the dominant species in the New World. Without them, we wouldn't be here today.
One of the cynodont line eventually became a mammal, and had it not been for the survivor through the cynodont line, mammals would not have existed and evolved, and nor would we. So we have a lot to thank the cynodonts for.
250 million years ago, life suffered a devastating blow and survived, with new species and new ecosystems. But the same kind of catastrophe that gave our earliest ancestors their chance could happen again. Eruptions like the one at Larky happen on average every 20 million years. Really big ones, like the Siberian Traps, are rarer. They happen every few 100 million years. But they do happen.
It might shock people to realize that the Earth can cause extreme devastation, and of course there's nothing that human beings with all their technology could do to counter that. So that if there were to be an eruption today on the scale of Siberian Traps, it would be hard to know how large numbers of human beings could protect themselves from it. So very likely there would be unbelievable death and destruction. Nobody would be safe.
But the biggest threat to mankind's future might not be a naturally occurring phenomenon. For the first time in history, the dominant species on the Earth is upsetting the delicate balance of its own ecosystem. Our production of carbon dioxide is having a catastrophic impact on Earth's systems.
We have the potential to release 2,000 or 3,000 gigatons of carbon dioxide to the atmosphere in the next couple centuries. When we look at the Siberian Trap volcanism, we're talking about maybe similar quantities of carbon dioxide released, but over millennia to maybe 1 million years. And so we're taking the whole Siberian Trap event and compressing it into the time scale of human activity, 1 or 2 centuries. And that's scary.
It's already causing the planet to heat up. And scientists fear that the runaway global warming of the past could happen again in the future. With more than 30 trillion tons of methane locked up as hydrates on the sea floor, the potential for another hydrate meltdown is as real today as it was 250 million years ago. But this time, we would have started it.
I'm sure that if we carry on what we're doing today in terms of pollution, we will cause a catastrophe, but how quickly is the big question.
The end Permian extinction was one of the most important chapters in the story of the evolution of life. It's an incredible thought, but it nearly wiped out life itself from the face of the planet. It ended the reign of the masters of the Earth, but it provided opportunities for others, survivors, who'd become our direct ancestors. Without the mass extinction event, all this probably wouldn't be here at all. In the next episode of Catastrophe, a massive asteroid smashes into the Earth and wipes out 70% of all life on the planet, including the dinosaurs.